Cool. Thank you. Thank you for the introduction. Great to see you all. Thanks for coming out to our talk on SkyRL. We originally open sourced SkyRL this June, and in the past several months, there's been a lot of exciting progress and updates. And so in this talk, we're excited to share with you all about our original motivation and design behind SkyRL and some of our plans going forward. And of course, this presentation is on behalf of the much larger SkyRL team and the many, many wonderful open source contributors to the project, many of whom are in the audience here today. So the way I wanted to start off this talk is give you a sense of the motivation behind why we built SkyRL and why we built it the way that we did. And the way that I want to do this is walk through a potentially oversimplified rendition of the eras of open source frameworks applying reinforcement learning to language models, where I'd like to take in particular the angle of observing the system requirements, or what the workloads actually looked like that informed the underlying system design of the RL framework. So to start, I'll call the first era RLHF. Maybe around this time last year, the major use case of applying reinforcement learning to LLMs was RLHF, where what the workload looked like is largely single turn generations, meaning that you often weren't giving the policy model multiple attempts at a problem and iterating with some environment, but rather you'd have your prompts or your conversation, and you would produce a single output from the model. And also you were only generating text. This is to contrast from today we see a lot of tool calls and interactions in rich environments. And then also relative to reasoning and agentic training, the context and rollouts were generally shorter. And so as a result of each of these characteristics of the RLHF workload, the open source stacks for RLHF at the time were built largely with a strong assumption of co-locating and tightly coupling the training and inference steps. Both of them are relatively short. Many folks in open source are often working at somewhat smaller scales than those in industry, and so it made a lot of sense to share the same GPUs between the two. And so that led to some really strong assumptions in the design of building these stacks of tightly coupling the two components. But then, O1 preview comes out. Academics are trying to reproduce reasoning. DeepSeek R1 comes out. Folks are now applying RL, not just RLHF, but they're trying to use RL to extend these long chain of thoughts for reasoning. And so many folks in open source would reuse those open source stacks that had been built for RLHF, but now the workloads looked a little different. As opposed to the shorter context or shorter rollouts, these long chain of thought rollouts were now much, much longer context. And so for the most part, because we were using these stacks, training and inference were still tightly coupled, but people started seeing, and we started seeing, that inference is increasingly dominating the training step time. And so this is the first pressure we felt that we would like to be able to put our inference workers on some other GPUs or independently scale the amount of compute we're dedicating to inference rather than training. And then the last nail in the coffin for us of this tightly located assumption was when we moved to start doing agentic training. So the workload was multi-turn, tool use, operating in some rich environment. And it really changed each of these characteristics. We're going from single turn to multi-turn. We're no longer just generating text, but we're now executing these like tool calls. The context has only grown longer and the rollouts only longer as we continue to extend the number of turns trained on. And then, of course, we now have environment servers. And so I think many folks, the naive way to extend this initial design to include environments, as many folks are running on the local CPUs of the training nodes that they have access to, which all feels a little silly now, but it was a naive first step. And I think it was also, the straw that broke the camel's back of encouraging us to reconsider the full RL stack design, as the system requirements had evolved quite dramatically from what was built for RLHF, and how the workload requirements had changed then from reasoning to agentic training. And so it was really in this context and our own experience in the lab at Berkeley of trying to train models across these eras that led us to start building SkyRL for our own work internally. And so the question raised, based on these observations, what do we want from an RL framework? And this will go along with the kind of The first thing we want support for diverse backends. So it's probably often the case that for any given individual, they maybe have their favorite training stack, favorite inference stack, in some environments they want to target. And we believe there shouldn't be a fundamental technical reason why one framework would not allow you to implement or extend or modify the training backend and the inference backend that you'd like to use. The next is we want to utilize the best hardware. And this is interpreting best along a few dimensions. It may be the most performant hardware for each of these three components. It may be the most available or the cheapest hardware. But really just what you want to be able to do is place each of these components on the hardware that best suits it for your use case, and to be able to independently scale the amount of compute dedicated to each of these components based on your use case. And really, I think what basically encapsulates these first two bullet points is the third, which is that you really just want well-defined public APIs between each of these components, which is just good software practice, but also it gives you the flexibility to implement your own custom backends so long as it adheres to the contract specified by the interface. And if you've already taken the effort to modularize these components, it becomes a lot easier to separately place, scale, and schedule each of the components. And so that takes us to our last point, that once you've nicely separated and modularized each of these components, they have well-defined APIs with a contract on their behavior, you'd like some flexible control flow. And this is where you start getting to enabling researchers or practitioners to express more flexibly the execution flow of your training loop, whether you're doing gRPO, whether you're doing PPO, whether you're doing some multi-agent system, where there are multiple policy models that are being updated. You'd like to be able to flexibly express each of these control flows. And so that basically takes us directly into the motivation for our design of SkyRL, which I'll start with a zoom out of the full architecture, and we'll dig through these one by one because it is a little dense. But what I wanted you to take away from this single slide is there's really just a few major logical components in the stack. I'll start with the trainer and generator, which again, I'll walk through it, but at a high level, the trainer is just responsible for receiving trajectories and rewards as input and updating policy model parameters. That's largely it. And then on the generator side, the generator just focuses on producing these trajectories and rewards for the trainer to go train on. But importantly, the generator is entirely agnostic to the existence of the trainer. And then finally, as we already discussed, there's the controller sitting above. So let's walk through some of these in detail to understand a little better what their responsibilities are, and then also what we have support for in the SkyRL stack now. So starting with the controller, as I mentioned, its responsibilities are largely managing the control flow between components and giving users a higher level abstraction with which to express the kind of training control flow they want to use. And this is also where you can make decisions about where various components in this loop are actually placed and scaled. This is where you can tweak the algorithm without actually caring about the details of the systems infrastructure of the training and inference workers themselves, and necessary things like spinning up and tearing down resources. Going to the trainer, as I said, its whole focus is update policy model parameters. It doesn't really need to know or care where these trajectories or rewards came from. They could have come from some like online learning, offline learning, could have been some continual learning from an online deployment. It really doesn't matter. Its goal is just update policy parameters based on trajectories and rewards. And so some of the features inside SkyRL now is we have first-class support for FSDP and Megatron. But we also, as we said, have, we want to enable folks to either make modifications to or implement their own training backends based on their use case. So we do have a training worker API that allows folks to integrate other backends. The stack supports, maybe you're running at a smaller scale, you have a few GPUs, and so you still need to tightly, you need to co-locate the training and inference workers, or maybe you're running at much larger scale, you're doing some asynchronous training, you can absolutely co-locate or decouple the inference and training workers. And then we just have like a rapid fire list of various things that many users like to have access to, which is LoRa training, MOE training. Like I mentioned, you're doing either single GPU or multi-node, whether you're using 5D parallelism for your MOE training. I think largely because we can make improvements both in performance and feature support in the trainer without thinking about or caring about what's going on in the other components, it has been quite easy to iterate quickly on some of these new features and performance improvements. And I also wanted to mention, unless you are I don't know, like a systems researcher, we have found that the vast majority of our users do not touch this component, which I think is actually nice for many of you who either want to operate at the algorithm level or the environment level. Ideally, you have to think as little as possible about what's happening in this trainer, and it should give you as few headaches as possible. Going to the generator, as I said, responsible for generating trajectories and rewards, and we have our canonical implementations of how to do this, but we also have code paths that are unopinionated and let you bring in your own custom ways of generating trajectories, and I'll talk about that a little more in a second. But really, the generator is a logical component that encapsulates both your inference engines, where you're getting rollouts from the model, and the environment, where you're actually interpreting the outputs of the model as actions and executing them. And so I would say this is the most often customized component. Folks are often either bringing their new tasks, or they have a new way of defining the agent loop or scaffold, or maybe they're doing some custom way of doing sampling with the inference engine. So because this is a popular place where users modify, I want to dig a little deeper into this SkyRL gem component, which is just one instantiation of the environment that you can use in the stack. So what we found early on among, honestly, just other students in the lab at Berkeley is many of them wanted to iterate quickly with some ideas they had on what I would call relatively simple tasks. This could be things like, I just want a search tool, or I just want a Python code executor tool, or maybe text to SQL. And so we have this gymnasium of environments expressed in the classic RL gymnasium step-based API that lets you pretty quickly just hack on a new task to both get a feel for the SkyRL framework, but then also iterate quickly on some new task you're trying to develop. So I won't spend too much time going into this. What I wanted you all to take away is that this is the lowest friction entry point to trying out new and fun, simple tasks on SkyRL. But because a large part of our motivation of building SkyRL, as I discussed before, is making it more modular, making it easier to poke around and modify and extend things, this is largely motivated because for our own internal use cases and for those of the many PhD students in the lab, we want to enable people to do research at each of these components while receiving as little a headache as possible from the rest. So we wanted to go through a few examples of how to modify SkyRL, really to try to convince you that it's quite easy, we think, and we hope you find it that way too. So the way I want to do this is start on this environment component. So I've told you we have the gym, I've told you we have this gymnasium API, but let's say you don't like our gym or you don't like the gymnasium API, you have your own way of expressing these things. So we have a few examples in the code base of integrations with existing either environment stacks or agent stacks like PrimeNLX Environments Hub or Terminal Bench or Mini Suite Agent or some implementations of the Search R1 recipe. And really all it takes to make that happen is first, the SkyRL generator or the SkyRL environment expects some input format, and each of these stacks expect a slightly different input format. And so there's often a quick conversion of data formats. SkyRL then passes this stack some OpenAI API compatible endpoint. So we're passing some URL for the agent stack and the environment stack to get rollouts from. And then we let the environment run and do its thing and generate the trajectory and reward. And then we got to convert that back into what SkyRL expects and into the format that the trainer expects to actually update policy parameters. So oftentimes this is like, I don't know, 30 to 50 lines of code and maybe half an hour to integrate each of these. So it's quite flexible and easy to do. I'll have Sumanth come give a few more examples, and then we'll talk a little bit more about the agent stack as well.
Okay. Yeah, I'm now going to talk more about modifying SkyRL and different other parts of SkyRL. So one example is trying to integrate this new method called FlashRL, which allows you to run your inference at 8-bit precision, whereas you're still running training in half precision. To do that, we're first kind of showing here how vanilla GRPO training looks like. And as you can see, the setup is simple. You're running maybe an inference engine like VLLM, as well as you have your trainer, both running in half precision like BF16. And you're using the vanilla GRPO loss function. With FlashRL, there's mainly like two modifications. Firstly, because you're running your inference at int8 precision, for your weight synchronization at parameter synchronization, you need to figure out some way to do online quantization to bring the trainer weights in BF16 to int8 weights for the inference engine. And the FlashRL authors also showed that this is not enough because you'll have a mismatch in the log probabilities between the inference and the trainer. So you have a correction factor in the loss, which is this modified loss called truncated impedance sampling that you use before updating policy model parameters. We've kind of integrated like both of these pieces into SkyRL so that you can try this out for the task you want to use. And yeah, there's a lot more details around like how this method works. There's details from the original FlashRL blog post that might be interesting for you to check out. There's also our example guide for like using FlashRL that you can take a look at. This is just showing here, like in terms of the graphs, that you can kind of recover the original performance with half precision training, while also achieving speed ups up to like 1.7x for a 32B model. But there's more details in the blog links if you're interested. Okay, I also want to talk about this recent blog post from Thinking Machines on on-policy distillation. And the core idea here is that with on-policy distillation, you're able to achieve like much faster convergence while training a small model on the task compared to RL. And it's actually pretty simple to kind of implement this in SkyRL. What I've shown here is like a custom trainer instance that's modifying like some kind of reward post-processing after we get the trajectories and rewards from the generator into the trainer. So we're modifying the reward here to use this reverse scale term that's comparing the teacher and the student probabilities. The details are too important for those of you who are not aware of on-policy distillation. But yeah, once you do that, there's just like two other modifications to make. You just implement like a simple custom advantage estimation function, as well as like a modified loss function. And you're pretty much good to go. And this kind of highlights like how algorithm modifications are actually pretty simple to make in SkyRL. Okay, so we'll now like switch gears a bit, and I'm going to talk about how we kind of train on like real-world agentic tasks and some of our learnings there. For context, I know these tasks are like, for some examples, like these are like deep research where the agent can use Google search and web scraping tools to answer like complex user queries. Another example is computer use, where the agent can use like mouse or keyboard tools in order to click around on a computer screen to perform some task. There's also the more popular Sui task, where the agent has access to like bash and file editing tools in order to maybe solve issues in a GitHub repository. There's actually a bunch of components that go into implementing these complex tasks. So for contrast, just consider three: a simple coding or math task for like a baseline in some sense, and also the two complex tasks like deep research and Sui. Now, obviously, for these different tasks, the tools that are available to the agent are different. For simple coding or math, you might use something like Sandbox Fusion from ByteDance, which provides like some simple process isolation. For deep research, the agent would have to use like search and web browser tools, and so you'd probably implement that. And for the Sui task, you'd have a bash and a file editor tool. There's differences in environment scaling for all of these tasks. And by environment scaling, I'm talking about how you parallelize like environment interactions for a large batch of trajectories during training. So for simple coding or math, you might just scale this up with Ray. For deep research, both the tools are probably like interacting with some kind of APIs. So maybe you'd implement some smart caching to speed things up. And for the Sui task, maybe, again, this depends on your setup, but one possibility is you kind of run containers for each trajectory separately in a Kubernetes cluster. There's also differences now in the optimal dispatch logic for different tasks. And dispatch refers to how you schedule and execute trajectories in a batch concurrently. I won't go into too many details here. We're kind of going to come back later. Oh, it looks like I missed agent scaffold. But yeah, let's talk about dispatch for a second. So for dispatch strategies, we're going to kind of come back to this later. But the idea is like there's differences for, say, like how you do this for deep research or SWE. For deep research, because like the environment execution is cheap, you might do something like async batch, whereas for SWE, like you might have to implement something more involved, and we'll kind of come back to it. Yeah, and there's also differences in like the agent scaffold, like we've shown here. So for example, for a simple task like coding, math, or deep research, you might use something pretty simple, like a simple React agent scaffold, whereas for the SWE task, you might use something more involved, like an open hands scaffold. You also want to kind of train and kind of use this agent stack in different generation contexts. So you might want to run and like use the same implementation and run evaluation and maybe even switch out with different training backends. Okay, so all in all, like if you come back to like the overall system diagram for RL, the generator, we broke it down into two components, environment as well as the inference engine. But for these real-world agentic tasks, this is actually not enough. Like we saw, there's complexities around orchestration, and we want to have some APIs and abstractions around this so that you can like customize this piece as well. So in summary, like the Gymnasium API, according to us, is not enough for these real-world agentic tasks, and we want to move beyond that. And we want like this layer to overall manage trajectory generation, taking into account both of these pieces, the environment and orchestration. And we've kind of built like this agent layer in SkyRL as well. Okay, so I've got like this very high-level overview of like some basic abstractions in SkyRL agent. Here, at least, it's like pretty straightforward. So you overall have this agent runner class that's kind of handling trajectory generation for the entire batch of trajectories. And it's going to use some user-specified dispatch logic to dispatch generation. And then for each trajectory, the agent will use like user-specified tools as well as the particular scaffold implementation. And during generation, your agent might be kind of sending away these tool calls, and you might use these tool calls, send them to environment servers, maybe even running separately from the training cluster. And overall, we want to support like modifying all of these pieces. So we want to allow researchers to customize all the components, like bringing your own agent scaffold maybe for a particular task, running generation in like different contexts, maybe even switch over different training backends, and maybe also like change like tool implementations, and also change just the dispatch logic for a given task, etc. Okay, so if I put this back into like the original training stack we looked at, it actually fits in a very simple way. Part of the reason is that we standardize around like the OpenAI API. So as you can see, like as usual, the trainer would send over prompts to the generator, again in like the OpenAI messages format, and then the generator, the agent runner would handle like the overall trajectory generation. And during generation, we talk with the inference engine, again, in the OpenAI API format. Okay, so now I want to talk a bit about modifying dispatch. And again, dispatch is around like scheduling and like concurrently executing a large batch of trajectories. And the optimal strategy can like change depending on the task. For computer use, you're executing like each LLM action in a VM instance, and you can also reuse this VM instance. So one example here is like you can have this async fixed pool strategy that's shown here that's doing just that. For these simple tasks like math, coding, deep research, execution is cheap. You can just parallelize all trajectories concurrently. And then for the SWE task, we've found that you can actually break down generation into like these 3 stages. One is like container initialization, and then one more is the code generation loop or the agent loop, and then the other is reward calculation, where you're running a test suite. And overlapping all of these like across trajectories is actually going to be more optimal for this task. So got a plot here of like comparing the async pipeline method as well as the async batch method for a SWE task. And even at small scale, for just training a 32B model with 512 trajectories and like 2 nodes, we're actually seeing like a 1.5x speed up, and this is going to be even better for a larger scale training run. So I won't spend too much time on this, but we've actually validated the agent stack on two of the tasks I talked about. One is deep research. Here again, like we're just showing like how a trajectory might look like. At each step, the agent can call the search tool or the web research tool. And we've validated training on a small training data set. And this is just showing like the reward curve. And we're also showing that like the reward curves match for two different training backends, the SkyRL train backend as well as the world backend. There's a lot more details for this, like in our blog in terms of the data set used and like some of our lessons that we learned when we went about implementing the tools for this task. Okay, I also want to talk about like our runs for training a SWE agent. Again, not many details here, but we're just showing like the training reward curve as well as the validation reward curve. And we're able to actually, with like an improved implementation of the open-hand scaffold, we're actually able to also beat the baseline like deep SWE recipe in terms of like validation accuracy. The baseline was about 28%, and we're able to reach 33%. And we've kind of already put this up in the agent stack on SkyRL for you to check out. Okay, now final comment on our roadmap. Two like recent features we worked on, recent releases that we've had. One is SkyRL TX. For those of you, maybe some of you have actually caught the talk that we had yesterday, but SkyRL TX is a new library that we've released that allows you to run a Tinker-compatible API on your own hardware. We also recently shipped LoRa support so that you can run efficient training while having the same accuracy. Some things we're working on in the short term are a better asynchronous training to be able to support like in-flight weight updates. And we're also working on memory management support so that you can incorporate summarization during training while still maintaining on-policy behavior. And we actually recently also made a Slack workspace for those of you who are interested in using SkyRL or just contributing to SkyRL, getting involved. This is the QR code for the Slack. Thank you.
Hello. Thank you, Sumanth and Tyler. I think we have a little under 3 minutes for questions. Yep. Raise your hand if you have one, and I'll come give you a mic.
Okay, thank you for the talk. I have a question. So basically, sometimes if I have a rollout and experience, I want to filter them or want to debug them or store in same database. How to implement? What is the best What is the best way to implement this logic in your framework?
Sure. So the question is like you have your trajectories rolled out. You want to do some analysis, debugging. You want to read through them.
Yes.
Things like this. Yes. So we do have a actually recently added like trajectory logger interface. By default, it'll downsample a bunch of the trajectories and send to wand B. You could alternatively like dump that to some like local CSV file. And then what I've done in the past is like I use some Jupyter notebook to like do some queries or some operating on those trajectories.
Yeah, but this logic is implemented in a trainer code or in a rollout?
This is in the generator side.
I see.
Yeah.
Okay.
Yeah. So after the batch of completed trajectories, you have your full GRPO group ready. You can like optionally pass through the trajectory logger to export some of them to 1B, dump it locally. Yeah.
Okay. Thank you very much.
Yeah, of course.
Any other hands? I got 2 mics. Anyone else?
Okay, thanks for the talk. I see this package is mostly optimized like for LLMs, both like with the algorithms and then also the inference. I was just wondering, like if you say you have a non-LLM, how much sense would it make to use your framework?
By non-LLM, do you mean like a vision language model or like truly a classic RL trained from scratch kind of model?
Let's say any IL trained from scratch, like any transformer, any model, basically.
Good question. I think it would make a lot less sense. I think I would opt for many of the optimized libraries built prior to RL for LLMs for these kind of use cases. One that we're like direction that we're interested in is to hear more from researchers in robotics who are using transformer-based models for some of their work, and whether there's something applicable in the SkyRL stack for them, but nothing yet. Yeah.
Okay, we have time for one more question.
Yeah. I had a question about how these trainer and inference modules are running. Like, for example, if I wanted to set a breakpoint in the trainer module to see what's going on in, let's say, PPO or GRPO, if I set a breakpoint in the trainer module, is the other components of the system running concurrently? Like, will they stop until I move on? Or like, could you describe like how those modules are structured in terms of, are they separate processes, or are they like separate threads within a single process? And unrelated question, is there any integration with Huggins Way's TRL, which is also quite popular for reinforcement learning? Thanks.
Yeah, so we manage orchestration with Ray, and specifically different workers of the trainer as well as different workers on the generator side are all running in different processes. If you do set a breakpoint in the trainer, you're like, I mean, it really depends on the stack, right? But right now, because we use Ray, like there's a good integration for just running breakpoints, and then so that would, in the typical setting with synchronous training, that would just pause training. And coming to your question on TRL, I would say like, you know, SkyRL itself is also like a similar generic RL framework at the same layer as like TRL. So like the training stack that we've built has some equivalence in terms of like functionality as to what you would get with trainers in TRL. So there's going to be a lot of overlap in terms of like the functionality there, if that makes sense. Okay.
Okay, looks like that's what we have time for. Thank you again.
Okay.
Thank you to everybody for attending.